So we're used to solving questions that involve motion in one direction. Like, for example, if we had a displacement to the east and then a displacement to the west and then a displacement more to the west, we can find out sort of our resultant displacement from the beginning to the end. We're used to doing that in one dimension. That's what we did in the first cycle. The second cycle, we're going to look at what happens if those aren't parallel to each other, if the directions aren't parallel to each other. So, for example, Janet walks 200 meters north and then 600 meters west. What is the displacement? So the displacement, remember, all it is from the beginning of the journey to the end of the journey. So it's that arrow there. We want to basically find the length of that arrow and the direction it's going in, right? So we can call this delta dt for total or resultant. Delta dr is sometimes used, but resultant and total are essentially the same thing. Resultant is just specifically to vectors when you add them up. So anyways, we want to find the length and the direction of that arrow, right? So if you remember the previous lesson on vector components, this looks actually very similar to a vector component question, right? Where we're given sort of the x and the y component, and we need to find the direction. So first of all, we can use the Pythagorean theorem to find the length of that vector, right? So delta dt is equal to the square root of 600 squared plus 200 squared. And if we do that in a calculator super fast, 600 squared plus 200 squared, and then take the square root, it's 632. 632 meters. All right, which makes sense. It's longer than either of those other sides. But then we need to find the direction. And the question is, where do we want to find the direction? Do we want to find this angle here? Do we want to find this angle here? Well, the key is we always want to find the direction from like the beginning, right? Because think about it this way. If you were to describe to somebody how to get from this point to this point, you wouldn't give them the angle at the end of the arrow. You'd say like, okay, so go this angle from north, for example, right? So essentially we want to find this angle here, this theta. So theta in this case, we know it's going to be tan inverse, just like the previous one, opposite over adjacent. In this case, opposite is the x component, happens to be. So it's going to be 600 over 200, right? And when we do this, tan inverse of 6 over 2 is 71.56. So I'll round to 71.6 degrees. Okay? Now, if we want to express this as a total answer, how can we do that? We could say delta dt, so the total displacement, is equal to, well, we're going to give it the direction, 632 meters. We're okay with 3 significant figures here. And then the direction. Now, the direction here, be careful. Is this the angle from north or from west? Well, if we think about our compass again, I'll just draw a compass here at the top of the page. North, south, west, east. We're sort of in this region here, right? And we're given this angle here. So that's going to be the angle north, 71.6 degrees, because that's what theta is. West. That's what that looks like an N. That's a W. So this angle here would be north, 71.6 degrees west. Now you might remember that I prefer the angle from the east or the west as opposed to from the north, right? So I actually prefer the angle sort of in here. It's easy to change that over though, because if we know that this angle is 71.6, this angle here is going to be the complementary angle. So we could also say that this is 632 meters, and we could do 90 minus that, and it'll be west. We just switch the west and the north around essentially. So it's going to be 90 minus 71.6, which is 18.4. So west, 18.4 degrees north, right? Because that would be, here, let's just do it in green. That would be this green angle there, right? So west, 18.4 degrees north. These two answers are both correct, right? Because that direction is the same direction, but I do prefer the one from the west than the one from the north, all right? For the reasons we talked about in the previous section. It's just easier to work with vector components if we can sort of all agree to start with the x component before the y component. Okay, let's look at question 2. Michael tries to swim straight across the river. He can swim at a speed of 3 kilometers per hour. The current is pushing him 4 kilometers per hour downstream. So just to sort of get a bit of a visual, let's assume this is the river. Let's assume this red dot is Michael. I'll call that M. So he's trying to swim across the river. But at the same time, so he's swimming across the river with a speed of 3 kilometers per hour, basically. That's how fast he's actually swimming. But the current is pulling him down, sort of downstream, if we assume that's downstream, at 4 kilometers per hour. The question is asking for what is his total velocity. So essentially what his total velocity is, we have to add those two velocities, right? Because he's swimming across, but he's getting pulled downstream. So it's going to be, his total speed is going to be more than those two speeds. We can't just add 3 plus 4, however, because they're not in the same direction, right? So part of that 3 kilometers is going to be in the x direction. Well, that whole 3 kilometers in the x direction, the whole 4 kilometers in the y direction. So the resultant is going to be some combination of those two. So the way we do it is the same as the previous question. We have our x component, which is 3 kilometers per hour. We have our y component, which is 4 kilometers per hour, right? And if we put them like this, where the tip of this one is at the tail of the next one, and we say we're going 3 kilometers per hour this way and then 4 kilometers per hour this way, we can find our VR. We'll call it R this time for resultant. We could call it T as well for total. I just wanted you to get used to both terms. So I want you to pause the video now, see if you can figure out that velocity. Remember, velocity includes direction. Pause it here, go. Okay, that's what I got. 5 kilometers east, 53.1 degrees south. Now, confession, I didn't give you a north, south, east, west in this question, right? I didn't say that downstream was south. I just sort of drew it that way, right? So I drew this. North, south, west, east. You might have drawn it differently. You might have assumed that those are different directions. Or instead of doing north, south, east, west, you might have used the directions downstream and across the river, right? You don't have to always call them north, south, east, west. They can be more descriptive than that. Either way, your answer should make sense. So if you did north, south, east, west, you should include a compass on your answer. Like if you were doing this on a test or something, just include that to show me, the person that's marking it, what your directions mean, okay? Always a good idea. And then your final answer makes sense. As long as your compass that you set up and your final answer are consistent with each other, you're fine. So that is the answer. And as we said, yeah, it's going to be faster. The combination of the across the river and downstream is going to be faster because sort of a combination of those two numbers. So in reality, this is the direction that Michael's going to swim. He's going to sort of swim on a diagonal because he's being pulled downstream as he's trying to swim across. So this is very useful information because it actually tells us the direction that he's going to travel. Okay, example 3. This is the last one on this page. Jeremy drives 7 kilometers south, 3 kilometers east, and then 1 kilometer north to get to school. It takes 10 minutes. Okay, so let's not worry about the average speed and the average velocity yet. Let's just try to calculate the displacement. So first of all, I'm going to try to get sort of an image of what he's doing. So he's driving 7 kilometers south. He's drawing 7 kilometers. 3 kilometers east. Oh, and I should do a compass here. Should just get used to doing that. North, south, west, east. Okay, 3 kilometers east. And then 1 kilometer north. Okay, I'm actually just going to move this over here to the other side. Let's erase that. And then the resultant, I'll do that resultant in, I don't know, what's a good color? Green. I'm going to choose a darker green. Oh, that's fine. Whatever. Green. So this is the resultant displacement from the beginning to the end of the journey. Sorry, that's not a 17. That's a 7. I don't know why that's not erasing. Oh, here we go. There we go, 7 kilometers. Sorry about that. So this, we're going to call this the delta dt for the total displacement, right? So how can we calculate that total direction? It's a little bit more confusing because it's not a triangle anymore. The shape that we have is no longer a triangle. It's a trapezoid. So if you're clever, you can maybe see that yeah, we can turn it into a triangle, right? We can basically look at it like this, and there's the triangle. This length of the triangle is going to be 6, and this one's going to be 3, and we could just use that. That's definitely one way to do it. The other way to do it is to think about the x and the y components separately. So we have these like y components here, right? These two y components, and we have this x component. And if we sort of wrote all those components out as separate vectors, it would look like this. So our first vector goes 7 kilometers downwards, right? Or south. So we could write delta d1, oops, let's not use yellow, let's use black. We could write this one as 0, -7. Remember that format, the matrix format? So there's no x part of it, it goes down by 7. For the second vector, we can express that one as having an x component of 3 and a y component of 0. For the third one, we can say that this one has an x component of 0, it doesn't go left or right, but it goes straight up, so 0, 1, it goes up by 1. So these are the matrix form, the components basically, of each of those 3 vectors. And our final answer is just going to be the sum of those 3 vectors. What do I mean by that? Well, all we have to do is add up the x components and add up the y components. So our final vector, delta dt, is going to equal 0, -7, plus 3, 0, plus 0, 1. Okay, where this is delta d1, that's our first displacement, this is delta d2, it's our second displacement, this is delta d3, right? And that has an arrow on top. If you think about it, if we just add up all the x components, so this one minus this one, it's going to give us this 6 kilometers, that's the difference between the two of them. And if we add up all the x components, sorry, these were y, if I add up all the x components, it's just going to be 3, that's the only x component. So if I add them up, that's all you have to do to add these vectors. Look across here and add up all the x's, and look across here and add up all the y's. So our total, actually, you know what, I'm going to do it on the side. Change my mind. Our total is going to be 3 for the x direction, and -7 plus 1 is -6 for the y direction. And that's sort of exactly what this triangle is here, right? It's just we've summed up the x components and we've summed up the y components separately. So now we can look at what that final thing looks like. And similar to the previous lesson, if we know the components, we can sort of figure out what the vector is that corresponds to that. So 3, -6, so that's 3 in the x direction. I'm just going to draw a triangle here. 3 in the x direction, and this is in kilometers, right? And then -6, so down in the y direction, 6 kilometers. And our resultant displacement is delta dt. That connects the beginning to the end. Of course, we need an angle here, so let's call the angle from the beginning of the path theta. So there we go. We know how to find that vector now. We did in the previous lesson, right? So delta dt is the length of it is the square root of 3 squared plus 6 squared, just using Pythagorean theorem, which is 3 squared plus 6 squared is 6.7. Well, let's round it 2 decimal places. We can round at the end. 6.71 kilometers. And our theta is tan inverse of 6 over 3, right? Opposite over adjacent. So 2 basically. Tan inverse of 2, which is 63.4 degrees. There we go. So our delta dt is just equal to 6.71 kilometers. And the direction is east, right? East is to the right, and then 63.4 degrees south. Goes to the south. So there we go. If we look at our original question, it only has 2 significant digits. So actually, I'm gonna write the answer in 2 significant. I'm gonna take away this 1 here. So it's just 6.7 kilometers. Let's do that properly, and we should do that for our angle as well. Angles and significant digits are a little bit interesting. For now, let's just not worry about it. I'm just going to round it to the nearest whole number. 63 degrees west. No, sorry, south. There we go. So that's the answer to part A. We found our total displacement. Okay? Can we find the average speed and the average velocity? So the average speed, remember, what is speed? Speed is just V average equals delta D over delta T. In this case, what's delta D? So this is for part B. Delta D, remember, is just the distance traveled. So in this case, it's just 6 plus 3. Oh, sorry, no, that's wrong. That's wrong. It's the 7 plus 3 plus 1, right? That's the total distance traveled is around this path. 7 plus 3 plus 1 is 11. So it's 11 kilometers. And the time it took was 10 minutes. And this is going to come out to units kilometers per minute, which isn't that good. Let's change it to kilometers per hour. So let's convert that 10 minutes into 60 minutes per hour. So we can do that conversion right in our calculation. So it's basically 11 times 60 divided by 10, which is 66. Oh yeah, it's just 11 times 6, which is 66 kilometers per hour on average. There we go. Part C asks us for the average velocity. So remember what velocity is. It looks very similar, but the velocity has the arrow over it. It's the displacement over time. And oh, I missed something. For my final answer for displacement, it should have the arrow over it like that. So our displacement, we just calculated, is 6.7 east, 63 degrees south. And then the time is the same, still 10 minutes, right? And again, we're going to convert that to kilometers. Oh, this should be, sorry, I missed here the kilometers. Can I move this over? How do I just move it over? I don't know how to do the, I'm learning still. I don't know how to just move it over instead of copy it over. So this is kilometers per 10 minutes, and then times 60 minutes per hour. The minutes are going to cancel out. So we just basically have 6.7 times 60 divided by 10, which is 40.2. And the direction, this is kilometers per hour, but we also have a direction, right, from the displacement, east, 63 degrees south. So our velocity, notice how it's a little bit slower, because remember, it's the displacement is less than the distance. And it also has a direction. So this is much more descriptive. The velocity is much more descriptive than just the average speed. This is like if you were driving along, that actually would be your average speed. This is just sort of the average time it will get from the beginning to the end of the journey in the same amount of time. So there we go. The thing to remember from this is when we have to add up the components of multiple vectors, we add up the x components and the y components separately. We can look at sort of the sum of all the x's and the sum of all the y's and just add those up separately. And then using that, we can find our final resultant. One last thing here. When I sort of drew this triangle, I said we're doing the x component first and the y component second. That's sort of what I've said is a good convention to use, because usually we do our x's before our y's when we do math. Just because of convention. If, though, we had gone the other way, does it make a difference? So if I had done the y component first, the 6 kilometers south first, would it change our answer? This is just a little bit of a thought thing. You don't need to copy this down. But if we had done our y, so if we started at the same point and done our y first, 6 kilometers, and then done our x, look what happens. We end up at the same point. So this illustrates an important point, which we'll talk more about in class. But basically the point I'm trying to illustrate here is that it doesn't matter which order you add vectors in. You're always going to get to the same place at the end, as long as you've added it all correctly. So the order you add vectors actually doesn't affect the outcome. Similar to if you're just adding and subtracting numbers, the order you add or subtract doesn't matter to the, or I should say just adding. The order you add numbers doesn't matter. 6 plus 2 plus 3 is the same thing as 3 plus 2 plus 6. Okay? So the same thing applies for vectors.